Okay, hey P-Chemsters, this is Mrs. Vanderlein bringing you Chapter 11, Part 3, Part 2 of the Blankwalle series here. So we left off and we were talking about dispersion forces, and more specifically talking about the van der Waals forces or the London dispersion. They're the same thing, aren't they? And if you recall, what does it depend on? It really talks about the molar mass. It's probably your most common difference, that the one is the greater molar mass. You have the more electrons, you have greater polarizability, therefore you have greater attraction, and you have, greater boiling point or whatever property you want to talk about. And so the other one we looked at in part one was that if you have more branches and it's harder then to get them close together, there's less attraction if you have things sticking out. And so that will also play with it as long as their molar masses are still the same. So the beginning of the next page asks a question. So why don't we look at that? So which one will have the highest boiling point and why? So go ahead and answer that and come back when you're done. All right, well, hopefully you got a chance to answer it. My answer is right here. It's iodine, all right? Why would that be? They are all nonpolar molecules, aren't they? Okay, so there's no oxygens or anything like that. So the only thing we're looking at is the molar mass. So iodine has a greater molar mass, therefore the greater number of electrons, therefore greater polarizability, therefore greater attraction, therefore higher boiling point, should be point, not poing. And so I wrote repeat after me. Why would I say that? Because you need to commit it to memory, all right? So has a greater molar mass, has a greater number of electrons, greater polarizability, greater attraction, higher boiling point. There's really 5 phrases in there, isn't there? So molar mass, number of electrons, polarizability, attraction, boiling point. Okay, so however you need to remember that, there are 5 things you need to say. Okay, so let's go on and talk about dipole-dipole. So dipole-dipole forces will exist in all molecules that are polar. So this is where we had to go back and look at chapter 10. What makes a polar molecule? And this is what the AP wants you to know, all right? It needs to be the big 4, okay? And it is not symmetrical. You can have other polar molecules, but you have to have an electronegativity chart handy. All right, and electronegativity difference would tell you polar versus nonpolar. They aren't going to do that for you. They're just going to expect you to know that if you have nitrogen, oxygen, fluorine, chlorine, and it is not symmetrical, then it'll be polar. The only exception to that is if you have like a nitrogen trichloride, they cancel each other out. But even if you have NO or OF2 or something like that, there's enough electronegativity difference between N and O and F and O to have still a polar bond there, okay? So they exist in all molecules that are polar, meaning, again, the big 4, and not symmetrical. You have to have the both and in there, okay? So polar molecules will have these partial positive and partial negative regions attached to each other. So the example is 2-propanone, okay? So 2-propanone. So does the AP expect you to know your organic molecules? The answer is no, it doesn't. This is a ketone, by the way. And so this is how you would probably look at the structure here. So if you're doing a loose dot diagram, you get something like that. And don't forget, you probably need to have your lone pairs around the oxygen and then put your hydrogens around the carbons down here, but I really don't care about that right now, okay? So why did I draw it this way, okay? Well, what's the shape of this? Well, how many electron groups do you have? I count 3. So what's the shape of this? Is trigonal planar. Hopefully you got that. Now, what else do you notice about this? Do you see a big 4? And yes, I do. What do you know about oxygen? It is very electronegative, okay? So this up here is my region of partial positive. I'm sorry, partial negative. Whoo, almost said that wrong. And down here is your region of partial positive. So what does that do for you? It sets up this dipole in this one molecule. So why do they call it dipole? Because how many molecules do you need to have an attraction? You need 2. All right. So if I were to take this molecule and clone it, which I did, And then I'm going to swing it around like this, and I'll swing this one around too, like this. What am I setting up? I am setting up two molecules with dipoles, and what's happening right here? What's happening right here? Ooh, got some attraction going. All right, and so when you get that region of positive, partial positive with the region of partial negative, that's the attraction. So that's what this is saying here. The positive end of the polar molecule is attracted to the negative end of its neighbor. So you need two molecules. That's why it's called dipole, dipole. All right, and each molecule needs to have a dipole, okay? And so that attraction means what? The intermolecular force is going to be even greater. You don't need to have an instantaneous dipole. You don't need to have just, electrons being polarized. You already have it when you have one of the big fours, okay? So which one of these molecules are going to have dipole forces? So what I would do if I were you is pause this, and I truly, truly mean this. Pause this, draw out the Lewis structure, and then determine if you have a big four and it is not symmetrical. Okay, so go ahead, and it'll probably take you a few minutes. Okay, so don't just watch me do it. You need to do this yourself. So pause this, work on this, see how you do. Okay, did you draw carbon dioxide this way? Hopefully you did. And what do you notice? Is it symmetrical or not? Well, it is not, because if you look, the dipole would be like vector coming out here towards the oxygen, vector coming out here towards the oxygen. What happens to those vectors? They cancel out. It is a non-symmetrical, I'm sorry, it is a symmetrical molecule. So even though I have polar bonds, it is not non-symmetrical if those two opposites make a positive or something. So that would be a non-polar molecule. So what about HCl? We're going to go across, okay? Is it symmetrical? No, it's not. If I have that vector, you're going to notice it's going to go to the big four. So this is going to be your partial negative, and this is going to be your partial positive. So this one will only have London dispersion. This one will have, this one will have both London dispersion and dipole-dipole. What about the next set? All right, so what about this one here? Dichloromethane is how you'd name it. What do you notice that? I drew it in its tetrahedral shape. Why would I do that? Because I'm trying to show you that no matter where you put your chlorines, if you swapped out these two and put the chlorine here and the H here, it is still not symmetrical. So when I put these side by side over here, all right, you'll notice that here's your partial negative and here's your partial positive. So this is has a big four, and it is non-symmetrical, therefore it is a polar molecule. So what kind of forces will this have? This will have London dispersion and dipole-dipole. So what about this one right here? Remember I told you, even though you see both big fours, all right, the electronegativity difference between fluorine and oxygen are great enough, it's still a polar bond. So this is bent. Notice again, I'm showing you its shape so you can see that it is not symmetrical and it has both big fours. So here is your partial negative and here's your partial positive. Very rarely do you see oxygen with a partial positive, but when it's paired up with fluorine, it will be. So in letter C, compare letter C to letter B. All right, here I have all four are the same hydrogens. Two things, it is both no big four, and it is perfectly symmetrical. So there are no vectors pulling things out. So the only intermolecular force here is going to be London dispersion. So what about SF4? If you drew it correctly, do you remember what name this is? It's not tetrahedral, is it? Because you have a lone pair right here. This is seesaw. So it is not symmetrical, and I see a big four. So yes, we do have these regions of partial positive and partial negative. So below the seesaw right here will be partially negative, where there's a lone pair will be your partially positive. So once again, it will have London dispersion. They all have London dispersion, but also it has dipole-dipole. Hopefully this is starting to make sense as to why did we have to learn all this stuff. Let's go to the next page. So hydrogen bonding is your third case of intermolecular force. It's your strongest intermolecular force, and I call it a special super doopy 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 doop case of dipole-dipole. What is hydrogen bonding then? It's your polar molecules, so it does have dipole-dipole, but it has NO and F, but not Cl, attracted to the H of another molecule. So how do you recognize this? You have to have NOF with a hydrogen attached directly to the NOF, okay? Why is chlorine not included in hydrogen bonding? Because of its size. It's bigger than NO and F, and that size interferes with the super-duper hydrogen bonding, okay? So it says intermolecular bond strength is higher than other dipole-dipole attractions, and examples will include ammonia, water, HF, and alcohols. And your basic alcohol has an OH group off of a carbon. Okay, so that would be an example, probably your more common example of your organic hydrogen bonding. There are other ones. Your carboxylic acids would also be included here too. So notice what's happening up here where I drew my water. Oops, sorry guys. Here's my partial negative, here's my partial positive. So what's actually happening here is that not just these parts are attracted, but it's actually attracted to the H of the oxygen here. It's also attracted, to the H over here. Whoa. And so anyway, that would be your hydrogen bonding. Okay, so let's look down below. So in the case here, notice I'm using HF as an example. So here's my H, here's my F. How did I know? Well, of all the molecules that have hydrogen bonding, HF is the only one that has 2 molecules. How do I know the H is on the left and the F is on the right? Well, F is your partial negative and H is your partial positive. Hopefully it wasn't a no-brainer. And what did I highlight right here? When the H bonds directly to F or N, the bonding atoms acquire a relatively large partial charges, giving rise to very strong dipole-dipole attractions between the neighboring molecules. Okay, so again, this is a super-duper case of dipole-dipole. Okay, so it's even stronger, therefore harder to separate when you boil it or something. So water has many important features because of this bonding, high melting and boiling points. Let's look at this chart here. What this chart is showing you is how special water is, okay? So notice the molar masses. So here, the molar mass is increasing, and notice the boiling points on the other end. So what do you notice about CH4, SiH4, GeH4, and SNH4? Notice that the molar masses are going up, but what kind of intermolecular force do these 4 all have in common? What's the only one they have? Well, they all have dipole-dipole. Do any of those have I said that wrong. All 4 of them have London dispersion. Do any of them have dipole-dipole? And the answer is no. So they all 4 have London dispersion, and that's it. Well, what do you know about H2S, H2SE, H2TE? Again, you aren't really expected to know this. I just do, all right? And so here you have London dispersion and dipole-dipole. Mrs. Vandewey, there's no big 4. I know, I get it, but I also know what their electronegativity numbers are, so I can just tell you with certainty that they do have dipole-dipole. And for that reason, notice that the boiling point is higher than these right here. Okay, so it isn't just molar mass alone, all right? They do have a weak dipole-dipole. They're not a strong dipole-dipole, let's put it that way. But what about water? It has dipole or London dispersion and dipole-dipole and hydrogen bonding. Now look at it. It is like the second lowest molar mass of all of these in the chart, okay? But look at its boiling point. It is so much higher than any of the others. Well, why is that? Because it has this hydrogen bonding. So I think this is a really important graph, really showing you the importance of having that hydrogen bonding. They also have high surface tension. So this is a great place to stop my video. What I would do is go to some of the other videos I linked on this particular Google Classroom assignment. Look for some of those other demos with surface tension and maybe jot down some of the ideas that you saw right here from those videos And then when you're done, come back to part 3. See you shortly. Don't wait to be great.